Hi everyone, today I will talk about single copy estimation of entanglement negativity. My name is Yu Zhou. I'm from Harvard University. This is joint work with Pei Zeng and Zhenhuan Liu from Q.Info University. You can see a recent work from Peter Zoller's group on this topic. This is the outline of today's talk. I will give the definition of the negativity moment, which can be measured by a many copy protocol. I will introduce our single copy protocol, which uses randomized measurements. Then I extend the single copy protocol to the bipartite case to quantify negativity moment. Finally, some statistical error analysis is discussed, and I also give the conclusion and outlook. First is the motivation. Recently, there are tremendous developments on the number of controllable qubits in several quantum computing systems. For these implementations, it's crucial to determine the prepared entanglement as a basis for further information processing tasks. Entanglement is an intrinsic resource in many quantum information protocols. Quantum tomography is a method to reconstruct the quantum states from measurement data, and one can calculate the entanglement measure from the reconstructed quantum states. However, it is an indirect method to quantify entanglement, and it is also resource-consuming, scaled exponentially with the qubit number. Entanglement witness is an efficient method to detect entanglement. It relies some pre-knowledge of the states. For example, one can construct some witness operators which acts as a hyperplane in the state space. Because it relies on some pre-knowledge, it can give a failure for the detection of entanglement. So one needs a direct entanglement estimation scheme without pre-knowledge. Let us introduce the log negativity measure for entanglement. Log negativity is defined as follows. We partially transpose the bipartite state rho AB. Then we quantify the negative part of the spectrum lambda k by taking an absolute value and finally a log function. Since log function is a little complicated, people would like to study the moment of this partial transpose depth matrix. However, the first and the second moment do not carry any information about the negative part. The first moment accounts for the normalization. The second moment accounts for the purity. So the third moment is the first non-trivial moment related to the negativity. And there are some numerics and analytical results to study this kind of quantities. And it shows that this quantity is also interesting in condensed matter physics to study quantum phases. In fact, the negativity moment can be expressed as observable on the three copy rho AB state. As shown in figure B, we put two three-order permutations on AB respectively. The three-order permutations are in different directions. One is clockwise, the other is anti-clockwise. This observable can give us the negativity moment. Compared with figure B, in figure A, the two permutations on A and B are in the same direction. It gives the three-order purity. As shown in figure A and figure B, we know that if one wants to measure the three-order quantity, like purity or the negative moment, one needs to prepare three copies of rho AB and do joint measurement between the three copies. So, in fact, it is challenging for this preparation and measurement, considering current quantum technologies, especially for the higher dimensional ones. In the following, I will introduce a randomized protocol which can just only use a single copy state to realize the same measurement. For simplicity, let us first consider a single copy protocol for three-order purity on a single particle state C. We just consider a rho, not rho AB now. And by symmetry, we consider the measurements M plus equal to W123 plus W132. First, let us briefly review the mathematical tool used in our protocol, which is the Weingarten integral for the higher random unitary. We use a k-Kobe unitary to do the k for turning channel on the observable x, and this u is sampling from the higher measure, and the result is some linear combination of permutation operators W sigma on the k-Kobe Hilbert space, and this C pi sigma is called the Weingarten matrix. Since higher measure ensemble is a continuous unitary ensemble, sometimes people use other sub-ensembles like Clifford to approximate the higher measure. So if some unitary ensemble is k design, it can give the same value for the k-fold channel. As shown in the previous page, the Weingarten integral on the random unitaries can give the permutation operators between different Kobe's. So here, we use some post-processing to virtually realize the Weingarten integrals along the work on randomized measurements. So our protocol is like this. We first prepare the state row. Then we randomly choose the unitary UD from some unitary ensembles to operate it on the row, and then we measure the state in the computational basis. Then we get some probabilities is conditional on the unitary u determined by the state row. By multiplying the probability 3 times and then averaging under unitary ensembles, we can get the Weingarten integrals on the 3 Kobe states. Here, the pictures give us the intuitions. Every line is a probability. We multiply, then it have the 3 Kobe states. Then we do some average. We can get the Weingarten integral and see there are some permutations between the states. In fact, we can do post-processing further by linear combination of different outcomes that we focus on this picture. From A to C, we introduce some coefficients OS determined by the outcome S. So we linear combination the outcomes with the 3-time multiplication of the probability. In the same time, the right-hand side of the equation also have some linear combinations. So by carefully choosing the OS coefficients, one can find that only the permutation, 3-order permutation survives. So we can have an equation to solve the coefficients OS by some turning channels. Finally, we find this expression for the O to reproduce the permutation W123 plus W132. Then we go to the bilocal protocol, which is related to the negativity moment. Note that, as we discussed before, on A and B, these 3-order permutations are on the different directions. One is clockwise, the other anti-clockwise. By some symmetry, we also make it a Hermitian operator. The measurement protocol and the post-processing is very similar to the single-party one. First, by evolve the state rho AB with UA tensor UB, where UA and UB sampling from the random unitary, and then we do project measurement on AB respectively. By many times of these routines, we can get the probability PAB conditional on UA and UB. Then similarly, we multiply this probability 3 times. Then we can get an effective turning channel on A and B respectively. And furthermore, we can combine the results of the output A and B to linear combinations. So similar as a single party case, now the problem is that can we find a post-processing strategy, say the matrix O, such that this function satisfies? Is it possible? In our work, we found that we can decompose this negativity operator into two parts. The first part can be done with the bilocal Turing channel. However, the second part, M plus AB, we should use the global random unitary UAB to evolve the states. Even we also found a no-go result to show that using bilocal unitary is impossible to find a solution to this function if O is a diagonal matrix on the computational basis. This kind of result is also helpful to study other quantities using local strategies. In fact, it answers an open question from previous work on whether one can use local unitaries to study higher order moments. In fact, the no-go result comes from the following reason. Because the three-order permutation 1, 2, 3 and 1, 3, 2 gave the same result for the product basis. So, based on this intuition, we introduce the bare state basis. It can give different result for the permutation depending on their directions. So we further decompose the negativity into two parts. And we found that the second part, which means that a Bell diagonal observable OBL can give the solution to this function. And considering our measurements, in fact, we do a bare state measurement between A and B after the UA at tensor UB evolution. In fact, our protocol also be used to quantify the total correlation. We define the total correlation in this kind of manner by using a fluidity measure between rho AB and its marginal. Let us focus on the nominator. We show that this quantity can also be write the permutation operators on the straight copy of rho AB. Then using the same strategy as we discussed for purity and the negative moment, we can transform this to a single copy measurement protocol. This is a diagram to show the permutation. In fact, in A, we permutate the 1, 2 part copy. The B, we permutate the 2, 3 copy. Then we discuss the statistical error about our protocol. In fact, the statistical error comes from two resources. The first is we do finite NU sampling from the random unitary. The second is that for every unitary U sampled from the random ensemble, we do finite measurement NM per unitary. We give an analytical framework to analyze the variance by constructing some unbiased estimators for our observables. And we found an analytical result for the asymptotic limit. And this D is the dimension of dA multiplied dB. When in the regimen D larger than NM larger than 1, which is the regimen of interest, we find the scaling like this. And if we keep the error like epsilon, we can just use NM to the polynomial of D and NU of 1 over epsilon square. Even though this scaling is still exponential with a qubit number, but it is better than tomography. The reason why we still have the exponentially scaling with the qubit number or the polynomial with dimension d is that we have no pre-knowledge of the state. The figure shows our numerical result for the bipartite Bell state mixed with white noise, and we change different NU and AM, and the numerical result satisfy our analytical prediction. Finally, let us give the conclusion and outlook. In this work, we use randomized measurement to measure negative movement at a single copy level. We introduce Bell state measurement to enhance the protocol. Our protocol can also use to extract total correlation, and we give a general framework to analyze statistical error. Considering future work, we can study higher order movements like the entanglement spectrums, and studying correlation hierarchy in quantum networks using randomized measurements. We can also apply this kind of tools to other quantities like the atom time order correlator, and to extend it to forming of boson system in the quantum simulator is also interesting. Thank you.